Alright, so we're going to start talking about magnetism, and we'll start in the same place in talking about magnetism that we did in both talking about gravity and talking about electricity, which is, let's start with magnetic forces. And again, let's sort of connect this as strongly as we can to the two fields that we've already discussed. So we said gravitational force acting on a mass in a gravitational field is given by this expression. So the gravitational force is a vector. It's equal to mass times the gravitational field vector. The electric force and a charge in an electric field, well, that's the electric force is given by charge times the electric field vector. And the magnetic force on a moving charge in a magnetic field is given by, so we use B to talk about magnetic things. So this is our notation for the magnetic force. It's equal to, well, here's our Q, but since we need it to be a moving charge, there's the velocity of our charge, and then B is the magnetic field. So Q is the charge of the particle, V is the velocity of the particle, and then B is the magnetic field. So a couple things. One is units, and you'll see that, well, the units for magnetic field is going to be, well, let's see, if I solve this for B, it's just going to be force over Q times velocity. So this is going to be newtons per amp meter. And then again, that has its own name, and we call it Teslas. So the SI unit for magnetic field is Teslas. And the other thing that obviously makes dealing with the magnetic field different is the fact that this is a cross product. So we don't have a cross product for either the gravitational force or the electric force, but we do have a cross product for the magnetic force, and that's going to change some fairly important things in terms of how we deal with magnetic force. All right, so the magnitude of the gravitational force, again, is just the mass times the magnitude of the gravitational field. And so what this equation is telling us is we said that all forces depend on an interaction between two objects. The gravitational force, well, mass, here's your test mass that feels a gravitational force, and then your source mass is causing the gravitational field. So the two masses you need to interact to have a gravitational force, there's one of them explicitly, and the other one is creating the gravitational field. For the electric force, again, now we need an interaction between two charges. So this, our test charge, it feels the electric force because it is sitting in the electric field that's caused by our source charge. So again, our interaction between two charges, one of our charges is written out explicitly. The other charge, our source charge, is buried in the electric field because our source charge is what's causing the electric field. Well, for the magnetic force, again, because it's a cross product, the magnitude of the magnetic force is a little bit different. So it's still Q, and again, we're using the absolute values here because if we're talking about the magnitude of something, this should always be a positive value. So this is going to be the absolute value of the charge. V here is the speed. B is the magnitude of the magnetic field, and then there's this sine phi term where again phi is the angle between the velocity vector and the magnetic field vector. And so if you think about this equation in terms of the structure we've been talking about up here, it has the same structure. What it tells us is that moving charges, so combine these two terms, moving charges feel magnetic forces. So I can have a charge, if I have a charge that's sitting in a magnetic field and not move, that's not moving, it won't feel a magnetic force. If I have something moving in a magnetic field that's uncharged, it won't feel a magnetic force. But if I have charge that's moving in a magnetic field, then sure enough, it will feel forces. And then moving charges also cause magnetic fields. Now, we don't tend to think about it when we talk about QV here. We don't tend to think about this. We think about this as a moving charge, but moving charges are really currents. And so the idea is that the gravitational force is an interaction between two masses. The electric force is an interaction between two charges. And the magnetic force is an interaction between two currents. We just happen to have a current that's caused by having a charge move around. That's our test current, if you will. And our source current is the current that's generating the magnetic field that our test current is moving around in. So it has the same structure as these other forces because all forces happen to be interactions between two objects. All right, so with this in mind, again, with the gravitational force as a vector equation, we were talking about the magnitudes, but now let's think about these three vector equations in terms of direction. So the gravitational force as a vector equation tells us that the force acting on this mass is always going to point in the same direction as the gravitational field at that location. The electric force here says, well, now you have two options because Q can be positive or negative. So the electric force acting on charge Q is going to point in the same direction as the electric field if Q is positive, or it's going to point in the opposite direction if Q is negative. The magnetic force, because of this cross product, it says that the magnetic force acting on charge Q is always going to be perpendicular to the plane defined by V and B. So basically any two vectors, in the same way that you say any 2 points define a line, any two vectors define a plane. And so when we talk about V cross B, basically the plane that these two vectors lie in, the magnetic force is always going to be perpendicular to that because that's what the cross product does. It gives us back a vector that's perpendicular to the plane defined by these two vectors. And if Q is positive, then the magnetic force will point in the direction of V cross B. If Q is negative, the magnetic force will point in the opposite direction as V cross B. But either way, the magnetic force is going to be perpendicular, whether in the direction of V cross B or opposite the direction as V cross B. Either way, the magnetic force will be perpendicular to the plane defined by these two vectors. All right, so again, that cross product gives us something a little bit different in terms of what's going on with the direction. All right, so how do the relative directions matter? Right? So the relative direction between the velocity vector V and the magnetic field. Well, here you notice that V on this charge, so I got a positive charge moving with the velocity vector that's in the direction of the magnetic field. Here I've got a positive charge moving in with a velocity that's opposite the direction as the magnetic field. And so when I think about this equation, I know that phi is the angle between the velocity vector and the magnetic field. Here, since these two vectors point in the same direction, phi is 0. Here, since they point in opposite directions, phi is 180. So if my particle is basically moving with a velocity that's aligned with the magnetic field, then phi is either going to be 0 or 180 degrees. Sine of either one of those is 0, and so there's no magnetic force. So if your velocity vector moves in the direction or opposite the direction of the magnetic field, there's no magnetic force that acts on your particle. It's going to continue to move straight at a constant speed. If, on the other hand, you start to change the direction of your particle, so it's no longer aligned with the magnetic field, well, now I have this sine phi term, and so here it will experience a magnetic force. And so again, I will use a right-hand rule to figure out the direction of that magnetic force. And so for a positive charge, V cross B is going to point up. So sort of the horizontal plane here is the plane that is defined by these two vectors. And so perpendicular to that means it's either pointing up or pointing down. V cross B points up, and we'll go over all our right-hand rules again in class tomorrow. And since I have a positive charge, the force is going to point in the same direction as V cross B. So here the magnetic force is going to point up on this charge, which means it's going to start curving out of this plane. So you notice that the velocity is in the plane, the force is perpendicular to that. So what the magnetic force always wants to do is it always wants to change the direction of your particle, not its speed. There's no component of the force that's that lies along the same line as the velocity, the force is always perpendicular to the velocity. So magnetic forces want to change the direction of charged particles. As we continue to move this velocity vector, so we fire our particle so that instead of being aligned with B, now it's actually perpendicular to B. So our velocity vector is now perpendicular to the magnetic field. Well, what we've done is we've made the angle between V and B as large as it can possibly get in terms of them being perpendicular, and that maximizes the force. So sine is maximized at 90 degrees. So when my two vectors are perpendicular, then the magnetic force is going to be as large as I can possibly make it. So what that means is that when the velocity is perpendicular to the magnetic field and phi equals 90 degrees, then my magnetic force is at its maximum value. If, on the other hand, phi is less than 90 degrees, then I don't have as large a magnetic force as I possibly could. All right, so the other way that we can talk about magnetic forces is, again, we said, well, really the magnetic force is an interaction between two currents. And so I can think about a current carrying wire or any current carrying conductor, and again there will be a current that will create a magnetic field, and if I put a second current into that magnetic field, I'll get a magnetic force. And so here we simply have some sort of wire that's carrying a current, and when we put that current into the magnetic field, we're going to have the same sort of structure in terms of talking about the magnetic force. So I here is the current, L is the length of the conductor segment, and then phi is the angle of the direction of the current along L and B. So this L as a vector always points in the direction of the current flow. And so basically this is our cross product. The angle we care about here is the angle between the direction the current is flowing and the direction of the magnetic field. And again, because of that sine term, I get no force if my wire is basically lined up with the magnetic field. So the magnetic force is 0 when the current flow is aligned with the direction of the magnetic field. I get the maximum magnetic force when the direction of the current flow is perpendicular to the magnetic field. So if I have a magnetic field that points to the right, a current that flows left and right will have no magnetic force. But a current that flows up and down will maximize the magnetic force acting on that current line. So those are the ideas that we're going to start playing with in terms of thinking about magnetic forces. And we want to be able to recognize the similarities between what we've already talked about with gravitational forces and electrical forces, but also the differences, and in large part those differences simply come because of that cross product within our definition.